Hello class, welcome to our first video over case study 2A titled Case Study 2A Notes Part 1, Intro to Case Study 2A. All right, so every time we have a new case study, we have the case study question and kind of help prompt us along. So go ahead, take a moment, read the preliminary info to case 2A, the case study 2A question. We're looking for any keywords in case study 2A. All right, so now that you've had a chance to read over that, I hope you were looking for some keywords, one of them being this word average. All right, so case study 2A is going to be our one population average hypothesis testing study. All the problems in case study 2A are going to be dealing with averages, which will affect the way we collect our data. Notice the data we collected is not a series of yes/no answers. It is a physical measurement that we took, being these pulse wave velocity values. All right, so this would be considered continuous data. What I'm going to do next is I'm going to go through the first 5 ingredients to hypothesis testing and go over hypotheses. If you would like to try this on your own first, you can just go ahead and pause me right here and give it a go. Otherwise, I'm going to start going through these one by one. Population is going to be all children with HGPS. The sample is going to be the 18 children with HGPS from the 2012 Boston Research Project. The variable of interest. How we define the variable of interest is that which is measured from the objects in our sample. If you notice up here in case question 2A, okay, what did we measure from these 18 children in our sample? We measured the pulse wave velocity values. So our variable of interest, simply pulse wave velocity values. And I went ahead and make a note of the units that we were being used there. Okay, parameter, symbol, the first thing to ask is what is the symbol going to be for parameter here? And whenever we're talking about averages, the parameter is always going to be mu. Now, when you write the parameter out in words, you want to make sure you incorporate the population, what it is that you're interested in, and also our keyword average. So our parameter will be defined as mu equals the average PWV value for all children with HGPS. The statistic, symbol and words. Again, start with the symbol for average. When we're talking about a statistic, will always be X bar. Okay, when we use the words, now we want to make sure we incorporate the words of the sample, what it is that we're interested in, and also our keyword average. So X bar equals the average PWV value for the 18 children with HGPS from the 2012 Boston Research Project. The next thing we need to do is find the value of the statistic. Now with this data set, we were given the 18 measurement, PWV value measurements that were taken on the 18 children. And from there, we can calculate an average by hand. So if you need to, you might need to go review descriptive statistics, or maybe you know how to calculate averages. We're going to add up all of those numbers, all of these numbers right here. We're going to divide by 18. And when you do that, you should get 12.44 meters per second. Okay, the next thing we need to do is set up the null and alternative hypothesis. So again, I just want to scroll back up to the question at hand. Among the children, a PWV value above 6.6 is considered abnormal. How strong is the evidence in the data regarding the claim that children with HGPS have abnormal PWV values on average? Okay, so that above 6.6, that's what's going to be incorporated into our HA. That's what it is that we're wanting to test here. So HO, mu equals 6.6. HA, mu is greater than 6.6. We're using mu because that's our parameter symbol when we're talking about averages. All right, so something I would like to go over with each of the case studies are type 1 and type 2 errors. So I want to actually practice writing type 1 and type 2 errors. Anytime I write an error, I always start with the definition and then just apply, well, what does that definition mean? Okay, so if I reject a true null, so if I reject HO and accept HA, then I'm claiming mu is greater than 6.6, when actually mu equals 6.6. All right, so I'm claiming the PWV value for all children with HGPS is greater than 6.6 when it is actually equal to 6.6. I went ahead and used the words from the problem instead of saying mu, I said average PWV value for all children with HGPS. That's how we defined mu right here above. Okay, a type 2 error is failing to reject a false null hypothesis. So when I fail to reject, it means I'm claiming that mu equals the 6.6 when actually it is greater than 6.6. So claiming the average PWV value for all children with HGPS is equal to 6.6 when actually it is greater than 6.6. The next step we have is test statistic, and that's where we're going to have to learn a new distribution. Now, before we go on to test statistic, I want to talk about these errors for a moment. So I had you write something down in your errors notes. One of the big takeaways besides the definition being how we choose what we fear, okay? If we fear a type 1 error, we pick a low alpha value, 0.01. If we fear a type 2 error, we pick a high alpha value, 0.10. If we're right in the middle, we don't know which one to fear, or we fear them both equally, we pick 0.05. All right, now I want to kind of go back to the top where we were initially talking about case study 2A. And I want to look at this piece right here, okay? So, well, I guess maybe I want to start the sentence before that. Do children with HGPS tend to have larger PWV values than children without the disease? That's what we're trying to test. That's our HA. Okay. If we reject HO and accept HA, then this drug, lonafornib, an enzyme inhibitor, may be justified as part of the treatment for children with HGPS. The drug is thought to be effective in lowering these PWV values and thus could prolong and increase the quality of life of a child with HGPS. Okay, so with that in mind, let's talk about these errors. And specifically, let's talk about some of the consequences that we could have with them. All right, type 1. We claim the average PWV value for all children with HGPS is greater than 6.6, when actually it is not. So keep in mind, when you've made an error, you don't know what comes after the when it is actually. We don't know that. So all we do is we report to whoever is running this test, hey, I did statistics and I claimed that the average PWV value is greater than 6.6. So they're gonna then go apply that drug, lonafornib, that they mentioned up at the top, okay? When actually the average PWV value is equal to 6. Okay, so what are the consequences there? You're giving a child a drug that they may not be qualified to take. If their average PWV value isn't actually greater than 6.6, maybe they shouldn't be taking the drug. Okay, so just to give you an idea of like consequences that come with these errors. All right, looking at type 2. Claiming the average PWV value for all children with HGPS is equal to 6.6 when it is actually greater than 6.6. Now again, keep in mind, you don't know the part that when it is actually. We don't actually know exactly what is going on in this population because we don't have the whole population. All I know is that After I did my statistical test, I claimed that the average PWV value was equal to 6.6. So I'm going to go tell who's ever helping me run this test, say, hey, we did not have enough evidence to reject HO and accept HA. We need to stick with HO for now, that the average PWV value is equal to 6.6. So then they're not gonna assign this drug to these children. But when actually I was wrong. So in this case, the consequence could be keeping this drug from these children that could benefit from it. Now, thinking about the consequences is part of it. And then you have to decide, well, which one of those consequences scares you more? And the idea of picking your alpha level and which type 1 or type 2 error scares you more will be different for every person. Okay, it might be different if this is coming from the point of view of a parent or the point of view of the CEO of the drug, lonanarfib, whatever it said, or if it's the point of view of a child with HGPS, okay? So when picking your errors of what you feel is worse or not, it is totally up to you. But you could see how with these errors in particular, there might be some serious consequences one way or another. Okay, so now that we're done talking about errors, our next step is Hey guys, our next step is the test statistic, which we need to develop a new test statistic for case study 2A. All right, so knowing that, we are going to use a couple theorems to help us out. Okay, the first theorem can be found on page 41 in the case study manual. Suppose a random sample of size n is collected on a variable. If the population of possible outcomes for this variable has a normal distribution, something tells me that might be important, with a mean of mu and a standard deviation sigma, then the sample mean x bar also has a normal distribution with mean mu, but with standard deviation sigma divided by the square root of n. Okay, using this theorem, what would our formula look like if we want to standardize x bar? Okay, in order to standardize x bar, we need our standardizing theorem. That's our z equals x minus mu over sigma formula. Okay, breaking that down into words, that means we take some variable, some normal random variable, you subtract the mean of that normal random variable, and then you divide by the standard deviation of that normal random variable. Okay, so our variable is going to be x bar. All right, that's what we want to standardize. And if you look back up at our theorem, it talks about x bar. It tells us, hey, if we have a sample of size n collected on some variable, x bar has a normal distribution. Awesome. With some mean mu and some standard deviation sigma over the square root of n. All right, so putting all those colors together give us that we have this formula z equals x bar minus mu divided by sigma divided by the square root of n. Okay, that's what it would look like if we standardize x bar based off of the theorem that is given above. Okay, so then I want to ask you, do you notice anything about that formula that could cause us trouble? The thing that could cause us trouble is this sigma, because we do not have the population standard deviation. We don't have anything about the population. We just have some stuff from our sample that helps us out here, okay? So what we're gonna do is that we're gonna let statistics estimate parameters. We're gonna let S estimate sigma. So we're gonna trade out this sigma in our equation for S. So now we have x bar minus mu divided by S over the square root of n. Now, making this estimation leads us to a second theorem that's going to help us out some. So suppose we have a random sample of size n that is collected on a variable. Suppose the population of possible outcomes has a normal distribution. Okay, something else that I feel is important. Normal distribution with mean mu and standard deviation sigma. If sigma is unknown and replaced by the sample standard deviation s, then the quantity t equals x bar minus mu divided by s divided by the square root of n has a t distribution with n minus 1 degrees of freedom. Okay, so right here we have found our test statistic for case study 2A. I'm going to zoom in for a minute and just kind of make a note that when you type this into your calculator, you're going to want to be sure to put parentheses around the top and the bottom. Okay, and that formula has a t distribution with n minus 1 degrees of freedom. The t distribution is the next new distribution we're going to learn about, and that's going to be the focus of our next video. Okay, now before I end this video, I want to talk about the requirements to use this t-test statistic. Okay. We use the sample standard deviation S to estimate the unknown population standard deviation sigma. That is, we use S to estimate sigma. Okay, make a note that this bullet is what I have underlined right there. Okay. The next requirement to use the t-test statistic is that the histogram is roughly bell-shaped. Okay, i.e. the sample comes from a normal or near normal distribution. Make note that that bullet is what I have underlined right here. Okay, so those two pieces that I have underlined, those are the requirements to let me use that formula. Okay, you know from previous case studies that the requirements are very important. So I hope it comes without saying that you have to know these. You have to know what these requirements are in order to even write down and plug into this formula. All right, so that is all for this first video. In the next video, I'm going to pick up with actually talking about, well, what is this t distribution that we got here?